Our next keynote presenter this morning is Professor Arsen Melikov from the Technical University of Denmark. Arsen is well known to the indoor air sciences community for his very significant contributions over several decades. So Professor Melikov is speaking this morning about advanced indoor air distribution.
Thank you, Richard. Good morning. My presentation will be on advanced air distribution. We may say advanced ventilation. But before continue, I want to ask you, can you hear me clearly? Yes or not? Yes. Well, I will first try to start with a critical review of what and how we ventilate today, and then suggest what we may do in the future. Ventilation is primary intended ventilation to provide clean air, to provide occupants with clean air for breathing. And of course, we have to do that in a proper way. In the left figure, we can see how we should not do it, because of clean air, which we supply, goes directly, or most of it goes to exhaust, and very little comes to the occupants. So we should avoid this. The second one is the better one. Clean air goes to each of occupants, not some, but to each of occupants. So we should try to do this in practice. How we do it today in rooms? So we have, I believe all of you know about mixing ventilation. All of you know about displacement ventilation. And we have diffuse ceiling ventilation. We have chilled ceiling combined with mixing ventilation. Then we have chilled beams, sometimes combined with radiant panels or without. We have underfloor ventilation, and we have several other ways to supply the air into the spaces. All of this almost, maybe except to some extent displacement ventilation, though in practice very often it performs as mixing ventilation. But all the remaining ones are known as ventilation by dilution. It is more appropriate, I believe, to say air distribution by mixing. And this is quite inefficient way to do it, to my opinion. And I will try in the next slides to justify why it is so. Well, let us take the example of a room. It has a chilled ceiling combined with mixing ventilation that distributes the air over the ceiling and then over the walls, floor, and then it goes to the occupied zone and reaches finally occupant. And today it is well documented that building materials such as wall painting, flooring, covering, carpets, or linoleum, or other materials, furniture, formaldehyde they emit, office equipment, occupants themselves, bioinfluence and exhaled air, all those emit pollution. And the purpose of ventilation will be to, as I already mentioned, to dilute this pollution and to provide occupants with better inhaled air quality. What we do today is that we try to ventilate the entire space. And of course it is inefficient because at least part of this space, 1/3 of it, we never use it. But in this 1/3, close to the ceiling, in fact, we provide the cleanest air. We supply, in order to improve air quality and reduce the pollution, we supply a lot of air into the space. And so we use a lot of energy, big air handling units, duct systems, and of course it's costly. Then what we do is quite inefficient. All this pollution that I already mentioned and defined, generated from the walls on the floor, we take it and transport it and bring it into the occupied zone, bring it close to the occupant. And then to improve the inhaled air quality, we supply more air and of course use more energy. And even if we do so, it happens that the people do not breathe clean air, simply because air supplied far away from them, from diffusers at the ceiling, by the time it reaches the breathing zone, it is already mixed with the polluted room air. It is also warmed. And also, these systems, when we try to ventilate the entire space, they should be slow. They should have limited control also. Sometimes, in fact, no control from the side of occupants. What today, in fact, we focus mainly. I listen many presentations, and if you open the standards, we read very much about ventilation rate. Nothing, or very little, we read about the airflow distribution, and it is very important. It has been, in fact, admitted, and it has been realized that it is so important many years ago. I have here a figure from a book which was published in 1899. So not last, but the century before that. And it shows exactly what that air distribution is important. This is a classroom, and we have a teacher, and the teacher generates or emits bioinfluence, polluted air, and because also generates the warm body thermal plume, all this pollution goes to the ceiling. In the same way, candles, at that time, there were no electricity. They used candles. They generate pollution, but also heat, buoyancy flows, and these flows move the pollution to the ceiling. Then, what we do is that we supply the clean air just where the pollution is, and we transport it and bring it to the occupied zone to the occupants. So, very, very inefficient way. And they advise us in this book not to do this, and many other examples. Nevertheless, what we do today is, most of the cases, is opposite of what they advised us. Let us see the standards. In standards, typically today, they recommend certain flow rate for comfort. And maybe 4, maybe 7, maybe even 10 liters per second per person. On the figure on the right side, it is shown % of dissatisfied occupants with perceived air quality as a function of the ventilation rate. Liter per second per person. Results from Asia, from Europe, and America show the same. They are compared. And when we supply 10 liters per second, we may get, according to this figure, about 15% of dissatisfied occupants. But if this is rather not ambitious goal, if we want to get less dissatisfied occupants, maybe only 5%, what we have to do is that we, according to these findings, we have to improve the supply ventilation rate, maybe to 20, maybe to 30 liters per second per person. Huge amount of air we have to supply into the space. A lot of energy we have to use. How about health? It was about 3 years ago when Sundell and co-authors, they published a review paper in Indoor Air Journal on ventilation rates. And their conclusion, based on comprehensive review of available literature, their conclusion was that we should supply minimum of 25 liters per second per person in order to minimize the health risk, S-based symptoms in spaces. This is quite a lot compared to what we need in average for breathing, what we inhale. What we inhale is about 0.3 liters per second. Close to 100 times more we supply, and as I said already at the beginning, the primary aim of ventilation is to provide clean air for breathing. So this is a question we have to try to solve. Often, ventilation air is used to its condition in order to maintain the right proper temperature and humidity in spaces. And today is well recognized. We have recognized that several of the characteristics of the airflow are important for thermal comfort of people, such as velocity, such as turbulence intensity, such as frequency of the velocity fluctuations. Airflow direction is important, air temperature is important, and so on. So it is very important that we are be able to control this flow and the characteristics of the flow. Unfortunately, we are not able to do this because the total volume air distribution is so that by the time the jets The flow, which will supply come to the occupied zone, it is in the fully developed region of the flow. It is recirculation air, and that is very difficult to be controlled. Complex interaction of airflow in rooms exists. It is not the ventilation flow that always decide or define the airflow pattern. These are thermal flows generated by heated objects, and the strength and the location of these heated objects is different. It may change in time, and this may affect the air distribution in the space. So as a result, occupants will be exposed to changeable environment. It is very difficult, in fact, to control this airflow interaction. And here the figure shows two examples. We have air distribution system on the left, well balanced to provide clean and cool air to the two occupants, and they will be happy. As soon as solar radiation starts to have impact and hit the window, it becomes warmer, generates thermal buoyancy flow, which together with the thermal flow from the computer and occupant becomes strong enough to discharge the ventilation flow to the opposite side of the room. So the person near the wall, far from the window, gets a lot of air, maybe in discomfort due to draft, while the person near the window is also in discomfort because of warm discomfort. So this is very difficult, in fact, to control. Well, I will now try to we know probably all, and I have heard all over, a lot of discussions on what is the goal we aim. And first, I believe most of us in this community, we believe that the goal is that we should have a healthy and comfortable and productive environment in spaces. And not just one of these elements, components, but all of them should be in place. But also, it is very important at the same time to have each occupant excellent conditions, not for average occupant, that does not exist. For each of these occupants, we may provide the best environment. And also, not instead, but also at the same time, we have to reduce the energy consumption. And then also, some of the practitioners may want to have flexibility in use of space. This is very important also to sell the area, floor area of the building. And then we have to make the HVAC system smaller, to take less size to occupy it from the building, and to be also cheaper and very easy to maintain, and so forth. So that we have several goals that we have to fulfill at the same time. And what I already told you, it is clear that these goals cannot be achieved with the total volume ventilation systems, with total volume air distribution, or generally with total volume indoor environment, which we aim to design today. So what we have to do is that we have to go ahead, and we have to find a new solution. We have to change. So some paradigm shift we should think about. So what I suggest is that we go from communal indoor environment to individual indoor environment, from the total air distribution to advanced air distribution. And we go from, instead of supplying the clean air to nobody, to supply the clean air to everybody in the room. And the question is that, will we be able to do this? So we have to follow important principles. And 3 of those principles I have listed. There should be more, but these are very important. First, of course, at the beginning, we have to remove pollution. We have to reduce pollution. Second, we have to supply the clean and cool air where it is needed, when it is needed, and as much as it is needed. And then also it is important that we have control over the air distribution. This is very important. And instead of air conditioning the entire volume in this large space, so we should condition only this place where this volume, where the occupants are. And already some years ago, there was introduced personalized ventilation on practice, where the part or all of the clean air is supplied from diffusers which are placed close to the breathing zone of the occupant, and the occupant has possibility to control the amount of the air which is supplied and also the direction of the flow, as occupant prefers. So it is documented that this type of air distribution improves inhaled air quality, thermal comfort. It improves, decreases the SBS symptoms, and it improves performance. So I will give you some results I'll show you from recent experiments we did when we demonstrated the importance of to consider both health and also comfort of the occupants. We tried, in fact, to validate what in standards today is recommended energy-saving strategy. Keep the room temperature 2-3 degrees higher above the comfortable temperature range, and then provide comfort occupants with thermal comfort by elevated air movement with elevated velocity. So in a climate chamber at 28 degrees and relative humidity of 30%, we exposed people to 3 conditions. One was with personalized ventilation, which is shown in the middle, that supplied clean air. And clean air with the temperature and relative humidity the same as the air in the chamber. The second cooling method we used was cooling fan. It moved the air, but it moved the room air, the polluted air in the room. And then we studied the response of the subjects to these 3 conditions, also without any cooling. And here are the results of this study. So first, on the left side is % dissatisfied subjects when they used either personalized ventilation, then they use fan, and no cooling at all. And with blue is perceived air quality, in red is thermal sensation. Both personalized ventilation and fan reduce dramatically the % of dissatisfied people. However, if we look on the right side of the figure, which is the SBS symptoms, in this case I have shown only difficulty to think and headache, how much it increased, how many persons reported after 4 hours exposure increase of these symptoms. And what we can see is that in case of personalized ventilation that supplied clean air, it was somewhere around 8-10%. It was much higher, almost twice, in case of cooling fan and no cooling. In fact, cooling fan and without any cooling perform very much the same. The conclusion is that even we should not aim only of one of these elements which I already discussed of indoor environment, comfort, but we should also care and take care about the health of the occupants when we apply solutions in practice. So future development, how I can see it, I believe that we should add to the background room environment, we should add microenvironment systems. And these systems might be different. They can be personalized. They can be personal. There is a difference between these 2 systems. Personalized systems are attached to building, to furniture. They may be used or calibrated for different people to be used because they may sense the new user that comes to that workstation. Personalized personal systems are those that belong to us and they're our own, and we can use it. They move maybe even with us. And I will show you some examples of this. And both those systems may be user-controlled when they can be calibrated in advance, and they may, when we start to use the system, they may sense us, and they may adjust the set points as we have used them before. But also they may be intelligent. So they may sense, they may predict, and they may provide, based on the physiological response of the body, they may provide the best environment. So it may be science fiction, but this is something not that science fiction, because the other day we listened about inverse CFD predictions, very much the same. And I will show you now examples of how we can easily implement advanced air distribution and benefit in practice. This is very often, at least in Europe, used system when we have a chilled ceiling combined with mixing ventilation that generates more or less uniform environment in occupied zone. So that environment is also very difficult to control and very slow response. I already explained. Now instead, we may combine the chilled ceiling, which is on the still the same as in the first example, but we can introduce personalized ventilation. And it will be very easy to incorporate the ducting in the floor. We today incorporate floor heating, and it will be very easy to incorporate also ducts that supply personalized air to each workstation. Plug and operate method. It gives quite a lot of flexibility to move the workstations. And it is so that under individual control of the occupant. If the occupant doesn't use this system or moves away, the system still provides a little bit air and additional air to the minimum required in the standards is provided by, as is shown by in this way, in this case by partition, it goes, and it still generates quite uniform environment in background environment. So this is preferred in this way. We can generate preferred environment. We can provide users with control and very quick response. It means that when we go from out, which is warm and humid, to our work station and come, immediately we turn on the system and it provides the cooling. And we may even later on, I will show you how we can control this flow, personalized flow, at the beginning to cool more and later less. So these results are reported in this conference in 2 papers. Here is another one, energy saving. I already mentioned it is important, and all of us strive to get energy saving. In this case, we combined chill beam, passive chill beam, to remove heat with personalized ventilation. Advantages are the same I already told you before. But if we keep the room temperature slightly high, maybe 27, 28 degrees, and still occupants will get very good thermal comfort, as the same as the comfortable, if the temperature was in the comfortable range. We may achieve energy savings up to, we have calculated up to 80% of the ventilation rate. I'm sorry, this is not energy saving, but 80% saving of ventilating air. And of course, this will mean maybe less, but still substantial energy savings. To control the airflow, I already mentioned at the beginning, it is very important that we are able to control the flow. And here is how, if we use advanced air distribution, how we may do it. We may design air supply devices that generate, that control not only the velocity of the supply flow, but also how it spreads and also its direction. So it's very efficient. When we come first after warm environment outside to our workstation, we first use a lot of air, very, very focused jet, which is in yellow shown. And then, after some time, it may be spread in order to cool over the body and get more benefit. This can be done either manually or automatically. It can be controlled. And free convection flow around human body. It is one of the flows that's important for the interaction of flow in rooms. And flow that is important for the quality of air we breathe, but also for our thermal comfort. So we should learn how to control it. In the figure in the middle, I have shown example how the personalized ventilation interacts with the free convection flow around human body, which is very strong, by the way. In order to penetrate this flow and to bring the clean air to the breathing, we have to supply a lot of personalized air with high velocity. So how we can improve this? We simply may apply so simple passive control strategy, a movable board that can gently simply be moved to and attached to the lower chest. So it will break the free convection flow, which will start again to develop above this board, but it will be very weak, and it will be very easy to be penetrated, much low velocity with much less flow rate. That will cause much less also disturbance, not only disturbance for the eyes and eyes comfort.
5 minutes.
Yes. Here is another case when we may use the flow curtain, as it is shown here, to entrain the exhaled air that is polluted, that might be infected, and move it upward. And we may control this flow. We have done CFD simulations of coughing occupant. This one is coughing, this one is exposed, and without curtain, after 5 seconds, we get a cloud of droplets, and some of those will be inhaled. When we have the curtain, we get very little of the droplets reach the breathing zone of the exposed occupant. We have, in hospitals, it is important to ventilate. Today, hospitals are ventilated with high exchange rates, but we use mixing ventilation. Some time ago, we developed bed ventilation when we have two devices attached on the two sides of the bed. The first device takes the room air, cleans it, disinfects it, supplied over the patient gently, guarding the exhaled air, which is polluted, might be infected, toward the other device, where it is cleaned and supplied upward as a curtain in front of the doctor. So it protects the patient, the doctor from the patient, from the air which is exhaled from the patient, but also it protects the patient from the air exhaled by the doctor, because it might be also infected. Of course, it's polluted. We have performed many experiments, and we report that local ventilation combined with background ventilation at 3 exchanges per hour is equal, provides same environment as background ventilation only at 12 exchanges. And we have quite many benefits in this way. We can get increased flexibility in space, use small air handling units, plug and operate principle can be applied. We can move the bed in the corridors, in another room, no problem. This is another example of advanced air distribution. We have a cabin which are densely populated, crowded space, and the risk of cross-infection is huge. And how we do ventilate today, this is a mixing ventilation. Now, we may do it in another way, maybe smarter way. We supply the air from the back of the front seat that goes to the breathing zone of the occupant and improves inhaled air quality. But this air also discharge the exhaled air by the occupant, by the passenger, backward to two air exhaust devices. And in this way, we may achieve, we have performed full-scale measurements in a section of a cabin. We have a cabin mock-up, and we document 40% decrease in the background concentration of exhaled air, and also 4 times cleaner air inhaled. Cooling and cleaning clothing. During this conference, cooling clothing based on evaporative cooling was reported. I will very quickly say the principle. With a very small pump, which is 0.12 watt power, we wet the outside of this T-shirt. The inner side, however, is not transparent for the air, so wet discomfort is not experienced. It is transferable, however, for the sweat, and because of the evaporate the water, so we get cooling. And we compare this, method with the cooling fan of 20 watts power. And what we can see, these are the results. Thermal sensation, we exposed people at 30-degree temperature and relative humidity of 50%, and cooling clothing, in fact, performed better than the cooling fan. This is wearable. The second last slide I will show you. This is the wearable personalized ventilation, personal ventilation, when we supply the air from the small nozzle around the microphone, very little, 0.4 liters per second. And these are the CFD simulation, depending how the air is distributed. When we supply it from front or from side, it goes directly or very close to the mouth and the nose. And we document in full-scale also experiments, 90% clean air inhalation. Can be used in hospitals, as it is shown here, call centers, and many other applications. Now I come to the last slide. This is the ladder of indoor environment. And at this moment, we are somewhere here at the acceptable level. This is what our standards recommend, acceptable environment. And this is also what the total volume environment may achieve, we may achieve. But we should go, of course, further. We should go up. We should go to the preferred environment, and here we should use the microenvironment, as we already discussed. And even further, we should go. We should go and try to design desirable environment. Maybe intelligent systems will help us for this. So there is a lot to be achieved. And I saw during this conference many young people attending, so you have a lot of work in front of you. Simply you have to be ambitious to achieve it. And also, this will require a lot of cooperation between many different disciplines. And they are all present at this conference. Amazingly, how many different disciplines are present here. So it's a huge potential for big success. Thank you very much.